Hello students. So this is the second video from the chapter Heterocyclic compounds. So in the last session, we had discussed about the heterocyclic compounds. What are heterocyclic compounds? And then the classification of heterocyclic compounds. Today we'll discuss about the aromaticity of pyrrole, furan, thiophene, pyridine, all these things. Right? Let us start with the pyrrole molecule. This is a pyrrole molecule. It is a 5-membered heterocycle with nitrogen as the heteroatom. Okay, this is the pyrrole. Let us see the aromaticity of pyrrole. Okay, now see what is the condition for aromaticity. So we have discussed this in the last session, but still once again I will just repeat. The first condition is the system should be cyclic. It should be cyclic. The system should be conjugated. Conjugated means there should be alternate double and single bonds. There should be alternate double and single bonds. For example, a single bond, a double bond, single bond, double bond, single bond. Such things should be there. There should be alternate double and single bonds. Or else lone pair of electrons, single bond, double bond, single bond. Such things should be there. That means all the atoms should be involved in delocalization. Delocalization of whatever the pi electrons or the lone pair of electron takes place. All the atoms should participate. For an atom to participate, each atom should have an unhybrid p orbital. It should have unhybrid p orbital in the same plane. So that they can participate in the delocalization. So system should be cyclic. It should be conjugated. Third one. It should follow Huckel's rule. Huckel's rule, it should have 4n plus 2 pi electrons. Where n may be 0, 1, 2, 3, so on. See, if n is 0, it will be 2 pi electrons. If n is 1, it will be 4 into 1, 6 pi electrons. If n is 2, it will be 10 pi electrons. If n is 3, it will be 14 pi electrons, so on. So it should follow Huckel's rule. So these are the main conditions for the aromatic or aromaticity. See, pyrrole is aromatic. Why pyrrole is aromatic? Because pyrrole has a cyclic system that is conjugated, lone pair, single bond, double bond, single bond, double bond, single bond, and 6 pi electrons are involved in delocalization. 6 pi electrons, 4 from this, 2 pi electron, 2 pi electron, and this lone pair also will be involved. So 6 pi electrons are involved, hence it follows Huckel's rule also. So pyrrole is also aromatic. Okay, let us see the orbital picture of this pyrrole. How actually pyrrole will, what will be the orbital structure of this pyrrole? Now, this is the molecule. Now, see, this carbon, there are 4 carbon and 1 nitrogen. This carbon is sp2 hybridized. So we have done it in this last session. If a carbon forms a pi bond, then that carbon will be sp2 hybridized. If carbon doesn't form a pi bond, that means all the 4 bonds formed by carbon are sigma, then that will be sp3. If it forms a pi bond, then it will be sp2. This carbon also has formed a pi bond here, so this is also sp2. This carbon also has formed a pi bond, so this also will be sp2. This is also sp2. Okay, this nitrogen involves its lone pair of electron in delocalization. So this nitrogen also will be sp2. That means if a nitrogen or an heteroatom, if it involves its electron in delocalization, then that will be sp2. This also is sp2 carbon, right? So if it is sp2 only, there will be one unhybrid p orbital. If there is one unhybrid p orbital, then these electrons may be involved in delocalization. If these electrons get delocalized in delocalization, then only it will follow the Huckel's rule. Then only the molecule will become aromatic, or else the molecule will be not be aromatic. So if the molecule is aromatic, then it will get extra stability. So this nitrogen involves its electron in delocalization, so that the molecule acquires a aromatic character. Okay, so this nitrogen also will be sp2. When I say hybridization is sp2, that means 1s have combined with 2p. When I say hybridization is sp2, that means 1s orbital has combined with 2p orbitals. If 3 orbitals have combined, you get 3 sp2 hybrid orbitals. If the hybridization is sp2, that means 1s and 2p have combined. If 1s 2p combines, that means 3 orbitals have combined. 1s and 2p, total how many? 3 orbitals have combined. If 3 orbitals have combined, 3 new orbitals will be formed. That means each carbon and also the nitrogen has 3 sp2 hybrid orbitals. Okay, and 1 unhybrid p orbital. Why? Because if you look at carbon outermost shell has 2s and 2p orbital. Carbon will have 2s as well as 2p orbital. If the hybridization is sp2 means 1s, and if 2p combine, so what will be remaining? 1 unhybrid p orbital will be remaining. So if when I say hybridization is sp2, it means that there are 3 sp2 hybrid orbitals and 1 unhybrid p orbital. See, if the hybridization was sp3, all the 4 will combine, so there will be no p orbital, unhybrid p orbital. Here the hybridization is sp2, that means 1 unhybrid p orbital remain as it is. So if you look at this, each carbon is sp2 hybridized, that means it has 3 sp2 hybridized orbital and 1 unhybrid p orbital. Here also it has 3 sp2 hybridized orbital and 1 unhybrid p orbital. Let us try to draw the structure of this. So carbon, and then the nitrogen atom. Okay, so carbon, and the nitrogen atom. Carbon, and the nitrogen atom. Okay, I will try it once again. We are not able to see this. Okay, so carbon, and then there is a nitrogen atom. So this is what the chiral structure: 4 carbon atoms and 1 nitrogen atom. Now, what is the hybridization of this? sp2. If the hybridization is sp2, that means this carbon has 3 sp2 hybrid orbitals. It has 3 sp2 hybrid orbitals. If it has 3 sp2 hybrid orbitals, right? If it has 3 sp2 hybrid orbitals, then what happens is here. Using 1 sp2, it forms bond with this carbon. It has 3 sp2. Using 1 sp2 orbital, because for formation of bond, orbital overlap is required. So sp2 of this carbon will overlap with sp2 of this carbon to form a carbon-carbon sigma bond. So it forms a carbon-carbon sigma bond first. Another sp2 of this carbon will form sigma bond with this carbon. Right? So out of 3, 2 carbon-carbon sigma bonds. One with this carbon, one with this carbon. There is another sp2 remaining. It will form bond with hydrogen. Right? Am I getting this? So similarly for this carbon has 3 sp2. So the hybridization is sp2. When I say sp2, there should be 3 sp2. So with 1 sp2, it will form bond with this carbon. Another sp2, it will form bond with this carbon. and another sp2 it will form bond with hydrogen. This is what happens. So similarly for this also, this carbon will form one sp2, two sp2, third sp2. This is also the same thing, one sp2, two sp2, and the three sp2. So nitrogen also the same thing, one sp2, two sp2, and this another sp2. So in pyrrole, all the carbon and nitrogen atoms utilize their sp2 hybrid orbitals to form carbon-carbon sigma bond. Now, when I say sp2, there will be one p orbital. So this has one unhybrid p orbital. This also has one unhybrid p orbital. This also has one unhybrid p orbital. This also has one unhybrid p orbital. And this atom also has unhybrid p orbital. So you know that nitrogen contains a lone pair of electron, right? So nitrogen unhybrid p orbital will have a lone pair of electron, whereas these carbon p orbitals will have an unshared electron. Okay, hope you are getting this, right? So all the carbon atoms are sp2. When the carbon atoms are sp2, that means they have 3 sp2 hybrid orbitals and 1 unhybrid p orbital. So carbon utilizes its sp2 hybrid orbital to form 2 sigma bonds with the adjacent carbon and 1 sigma bond with the hydrogen. And unhybrid p orbital contains an unshared electron. Okay, I will draw the structure once again so that we will have a clear idea regarding this. Okay, so we have carbon, 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 and then nitrogen. Okay, so using sp2, it forms a bond with this, and another bond with hydrogen. Bond with this, another bond with hydrogen. Bond with this, hydrogen, hydrogen, and bond with hydrogen. Right? Now, so this carbon has 3 sp2 hybrid orbitals, 1 sp2, 2 sp2, third sp2. So this carbon also 1 sp2, 2 sp2, 3 sp2. This carbon 1 sp2, 2 sp2, 3 sp2. So this is the sigma structure. Now, each carbon and the nitrogen atom has one unhybrid p orbitals. I will just draw this unhybrid p orbital. This is unhybrid p orbital. This also has unhybrid p orbital. This also has unhybrid p orbital. This also has one unhybrid p orbital, and this atom also has one unhybrid p orbital. We're getting this, right? Now, so these nitrogen contains what? A lone pair of electron in this p orbital, and these carbon atom contains one unshared electrons. Now, these p orbitals are in the same plane. They are in the same plane. So these electrons, I mean 4 electrons on carbon, that is, and one lone pair. Lone pair means 2 electrons. Total how many electrons? 6 electrons. They get delocalized. Okay, the 5 p orbitals. There are 5 p orbitals, 4 carbon and 1 with nitrogen, which contains total how many electrons? 6 electrons. See, 4 in this carbon, 2 in this. So they are in the same plane. They delocalize these 6 electrons. And this delocalization of this pi electrons imparts aromatic character to this pyrrole. It will impart an aromatic character to pyrrole. Why it will impart an aromatic character to pyrrole? Because it follows Huckel's rule, 4n plus 2 pi electrons, right? Total there are 6 electrons. So the molecule is cyclic, there is a conjugation and all those things. So hence it imparts an aromatic character. Okay, so we can show that delocalization, there is a delocalization of these electrons. So pyrrole can be best represented like this. You can represent pyrrole like this. This is the nitrogen atom. NH, 4 carbon and nitrogen, double bond, right? And this nitrogen has one sp2 hybrid orbital containing a pair of electron. Okay, or else when write it like this. NH. So there is delocalization of this 6 electrons. So this is the orbital structure of pyrrole. So there is a delocalization of electrons. How many electrons? 6 electrons. In all the atoms are involved in delocalization. This imparts an aromatic character to pyrrole. So hence pyrrole is aromatic, and this is the orbital structure. Okay, so all the molecules have similar type of the structures only. So if you understand this, the remaining molecules will be easy. Okay, so we will just go for the another molecule, that is furan, and let us try to go through this. Right, now let us discuss furan molecule. Furan is also 5 membered, but instead of nitrogen it has oxygen atom in the ring. Okay, so this is furan. This is furan. So it does not have a OH here because oxygen valency is 2. There nitrogen it was valency was 3, so it was NH. So it will be just this molecule. Here also all the carbons are sp2 hybridized only. There is a double bond, so hence sp2, 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 sp2. This oxygen is also sp2 only. Why this will be sp2? Because it wants to involve one pair of electron into delocalization. If it has to involve one pair of electron into delocalization, then it should have one p orbital which is not involved in hybridization. I mean one unhybrid p orbital. It should have a p orbital that is in the same plane. That is why it will be sp2 hybridized. Okay. When I say sp2 hybridized, this carbon will have 3 sp2 hybrid orbitals and 1 unhybrid p orbitals. This also will have 3 sp2 hybrid orbitals and 1 unhybrid p orbitals. Okay, I'll just represent the structures. Okay, please. So it has 4 carbon atoms. I will draw carbon atoms like this. 1 carbon. This is another carbon. Okay, I will draw the 3rd carbon here. 3rd carbon. I will draw 4th carbon here, and the oxygen atom here. So anyway you can draw it, but it will be easy for me to show the orbitals. That's why I have taken oxygen like this. That means I am drawing the molecule like this. Like this is what I am drawing, right? So 4 carbon atoms and 1 oxygen atom. 1 oxygen atom. Now, so the hybridization is sp2. sp2 means it has 3 sp2 hybrid orbitals. So with 1 sp2 it will form bond with this carbon. Another sp2 it will form bond with this carbon. Another sp2 it will form bond with hydrogen. So similarly for this carbon will form bond with this, bond with oxygen, and then hydrogen. This also the same thing, carbon, then hydrogen. This also the same thing, hydrogen. So this also has 3 sp2. Out of 3 sp2 it has formed bond with this carbon and bond with this carbon. That means out of 3 sp2, 2 sp2 they form carbon oxygen bonds. Okay, this also has sp2 hybridization. That means it also has 3 sp2 hybrid orbitals. So when I say 3 sp2, out of 3 sp2, 1 sp2 is utilized here, another sp2 is utilized here. So 1 sp2 is remaining and 1 unhybrid p orbital is remaining. 1 sp2 is remaining and 1 unhybrid p orbital is remaining. Right now, so we know that oxygen contains 2 lone pairs of electrons. Oxygen atom contains, when it is bonded, it contains 2 lone pair of electrons. So it has 1 sp2 and 1 unhybrid p. So it has 1 sp2 hybrid orbitals. This is sp2 hybrid orbitals. sp2 hybrid orbitals are represented like this, with a large lobe and with a smaller lobe. Okay, and it has one p orbital. It has one p orbital like this. P orbitals are dumbbell shaped like this, right? So it has one p orbital. So oxygen contains two lone pair of electron. One lone pair of electrons will be in sp2 hybrid orbital, and one lone pair of electron will be in anhybrid p orbital. See, total there are 4 orbitals, 3 sp2 and 1 anhybrid p. Out of 3 sp2, 2 sp2 they form bond with this. One sp2 contains lone pair, another sp2 also contains lone pair. Oxygen contains 2 lone pair of electron. Now, this carbon has also one anhybrid p. This carbon also has 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 one anhybrid p. Right? Anhybrid p. Bond should be shown like this. Right? So this carbon also has one anhybrid p. So anhybrid p are dumbbell shape orbitals. Right now. So these carbon contains an electron each here. An electron each. So what happens is here. So these 4 electrons and these 2 electrons, they involve themselves in delocalization because these are in one plane. These electrons that are present in sp2 hybrid orbitals are perpendicular to this. So they cannot involve themselves in delocalization. So out of 2 lone pair of electron, 1 lone pair of electron is involved in delocalization, and the remaining 1 lone pair which is in hybrid orbital is not involved in delocalization. So these 6 electrons, 1, 2, 3, 4, 6 electrons, they involve themselves in delocalization using these 5 orbitals, p orbitals, which are in one plane. So since there is delocalization and it follows Huckel's rule, so this imparts an aromatic character. It imparts an aromatic character to this molecule. It imparts an aromatic character to this molecule. Okay. So when there is an overlap, upper lobe as well as the lower lobe both overlap. That's why this is shown like this. So the molecule can be best represented like this. Can be represented like this. So this is a furan molecule which indicates there is a delocalization of electrons, and the one lone pair of electron that is present here, which is not involved in delocalization. Okay, so this is about the furan structure. Okay, so we have another structure, another molecule called as thiophene molecule. Thiophene molecule will have the same arrangement as this. Thiophene, instead of sulfur there will be, instead of oxygen there will be sulfur. The arrangement is same. The arrangement is same. Instead of oxygen there is sulfur. So the arrangement is same. Okay, hope you got an idea regarding these things. Right. Now, another molecule, that is pyridine. Let us go for pyridine. Pyridine is a 6-membered heterocycle. Okay, these are all 5-membered. Thiophene, furan, these are all 5-membered. But pyridine is a 6-membered of heterocycle. Thiophene, you go through the thiophene. Okay, thiophene has the same structure as furan only, because oxygen and sulfur belong to the same group. I mean same family. They are same family, one below the other. So sulfur also will be having 2 pi electrons, 2 lone pair of electrons. Out of 2 lone pair of electron, one lone pair of electron will be in p orbital, which will be involved in delocalization. Another electron will be present in the hybrid sp2 orbital, which will not be involved in delocalization. Okay, pyridine. So pyridine, this is the structure for pyridine. Let us check the hybridization. sp2, because there is a double bond. sp2, there is a double bond. sp2, sp2, sp2. This also will be sp2. Right? So here carbon atom and the nitrogen atoms are sp2 hybridized, right? Now let us try to picture out the orbital picture of this pyridine. Okay, pyridine contains how many? 5 carbon and 1 nitrogen. I'll just draw the carbon. 1 carbon. This is the second carbon, third carbon, fourth carbon, fifth carbon, and there is a nitrogen atom. Right? Now, so since the hybridization is sp2, so it will have 3 sp2 hybrid orbitals and 1 unhybrid p as usual. So 3 sp2 hybrid orbital, 1 sp2 is utilized to form bond with carbon, another sp2 with this carbon, another sp2 with hydrogen, right? sp2 with carbon, sp2 with this carbon, and sp2 with hydrogen. Same here. Same here. Same for this carbon. Nitrogen now. Okay. So this nitrogen has 3 sp2 hybrid orbital. Out of 3, 2 are utilized here. One to form bond with this carbon, another to form bond with this carbon. You all know that nitrogen contains a lone pair of electron. So the another sp2 hybrid orbitals will bear this lone pair of electron. Okay, that means this lone pair of electrons will not be involved in delocalization, because for a lone pair to be involved in delocalization, that should be present in hybrid orbital. I mean unhybrid p orbital. Now let us see. So this is about the 3 sp2. This is about the 3 sp2 of nitrogen. One it forms bond here, one it forms bond here. Another sp2 contains a lone pair of electron. Now each atom contains one unhybrid p orbital. So let us see for the unhybrid p orbital. Unhybrid p orbital, 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 and the unhybrid p orbital. Right? All these are in one plane, so they participate in delocalization. Each p orbital contain one electron. See, total how many electrons are there? See, actually nitrogen contains one lone pair, but the one lone pair of electron is present in sp2 hybrid orbital. It will not be involved in delocalization. Now, so there are total 6 electrons and 6 p orbitals. So these 6 electrons, they get delocalized here. So these 6 electrons get delocalized into these orbitals. Right? So this imparts aromatic character to the pyridine. See, here in pyridine, the lone pair of electron that is present on nitrogen is not involved in delocalization. So pyridine can be best represented like this. It can be represented like this with a lone pair of electron that is present on nitrogen. Okay, so this is the orbital picture of pyridine. So students, so this was the orbital picture of the molecules that is there for syllabus: thiophene, furan, pyrrole, as well as pyridine. Okay, in the next session we'll be discussing about some of the reactions of these heterocyclic compounds. Okay, thank you.